Okay, this is the last video on sequencing series. It's more about kind of exam questions and some useful tips and tricks. We're going to start off with modeling, which is essentially worded questions involving sequencing series. These can be really tricky. You need to spend time reading them. If you look at the question that's on the screen right now, you can see there's a lot of words and numbers, and some of the numbers are not as useful as the other ones. So it's really important that you spend time clearly underlining, trying to extract the right information. So let's have a go at this question. I recommend you pause it and read it. Okay, so what information can we get from this question? Well, it started 20 years ago. In year one, her annual salary was $17,000. Her annual salary increased by, and I think that should say £1,500 each year. So that her annual salary in year two was $1,850. So increasing by 1,500. So that means her first salary was 17,000, and that's A. And it's increasing, so it's arithmetic, by £1,500 each year. Note that I'm dropped the units, but they would have to be in any final answer because this is in context, so the answers should be in context. We're told it's an arithmetic sequence, and it continues until she reaches her maximum annual salary of $32,000 in year K. We've got to find the value of the constant K. We've got to find when does her salary reach 32,000. Now, the important thing to note here is that she will be in total earning each amount and adding it together. But this is not talking about adding it together. This is not talking about something I can see that's coming in question B. This is talking about what is her actual salary. So we are interested in when is her salary 32,000, and that is going to be the kth term. That is going to be 32,000. And the kth term, as we know, is going to be A plus K minus 1 times D, which is 17,000 plus K minus 1 times 1,500. And now it's just a case of equaling that to 3,200. So the formula that we're trying to solve, the equation we're trying to solve, is 32,000 is equal to this, which is 17,000 plus 1,500K minus 1,500. So putting that onto the other side, I am going to get that K is equal to 11 when I solve that equation. Actually, should we do it? I've skipped and just used the fact that I know the answer. Let's just do it properly and actually work it out. So firstly, I'm going to take that away from there, and I'm going to get we'll get 1,500, 15,000 plus 1,500 equals to 1,500K. And actually we can kind of see that that's 10 times plus 1 times, so we can see that we get K equals to 11. Okay, so in year 11, that's when her salary reaches that. Her annual salary then remained at 32,000. Okay, so calculate the total amount that Jess earned in the 20 years. So that means that for years 1 to 11, we have this arithmetic sequence. And for years 12 to 20, it is just 32,000. Although, as you actually spot, it's actually in years 1 to 10, it's the arithmetic sequence, and actually from 11 to 20, it's 32,000. And we're heading towards the biggest difficulty in these questions. The biggest difficulty is making sure that we get the numbers right. So 1 to 11, how many terms is that? 1 to 11. Is it 11 terms? Is it 12 terms? 12 to 20. How many terms is that? Is it 8 terms? Is it? Think about it and pause the video. Okay, you should have done a little bit of thinking, and hopefully you could see that, yeah, this is 11 terms. And this is actually 9 times 3,000, 32,000. Now, if the numbers are relatively small, I actually don't think there's anything wrong with using your fingers. So if you were trying to work out how many times are there between including 12 and 20, then just count on your fingers. Go 12, 13, 14, 15, 16, 17, 18, 19, 20, and you'll see that there are 9 lots there. But you might have bigger numbers, and in which case just kind of try to get a feel of it, but it's going to normally be, well, 20 minus 12 is 8, and then you add 1 because you're adding both ends and not just one end. So there's the ways to go about it. So we know that we're going to work out the sum of an arithmetic sequence, the first 11 terms of an arithmetic sequence, and then we're going to add 9 times 32 on. So we've got A is equal to 17,000. And we've got D is equal to 1,500. And I want to know what S11 is. Well, the formula, which is in the formula book, and you should have, but you shouldn't need to look in the formula book, you should know it by now, is that. And we want to plug in the values of this. So we get 11 over 2 times 17,000. Plus 11 minus 1 times 15,000. And plug that into our calculator, which is going to give us this. So it's fraction 11 over 2. 2 times 17,000 plus 11 minus 1 is 10. Times 1,500, and I get 269,500, 269,500, and then I want to add, so total in 20 years is going to equal 269,500 plus 9 times 32,000 of the 9 years where they just earn 32,000. So I'm going to just add to that 9 times 32,000 to get a total of 557,500. So giving it units for the final answer, 557,500. £557,500 is the total earnings. It's a lot of money. But I guess it's across 20 years. So, yeah. Okay. So I told you that there's some really easy mistakes to make. And this is another example of that really big mistake about counting the end and the start. So I'm going to do this question. We've got a person, Mrs. Epoch, invests £1,000 into a savings account on January the 1st, 1970, and it pays 1% compound interest at the end of each year. In what year can she first afford to buy a car worth £1,250? So, let's start. First term is 1,000. And if you compound interest means that what we want to do is find 1% of that and add it on. So that's the first term. The second year, we know that we need 1,000 plus 1% of 1,000. So I guess you could write that like this. But actually, a better way of writing that is like this. And in A3, since it's compound interest, we want to multiply that by 1.01 again to get this. And at this point, you might see that what we've got is a geometric sequence. This is geometric. with A is equal to 1000 and R is equal to 1.01. We want the sum, the nth term, not the sum. We want the amount to be 1250. So what we want to do is we want the nth term of this sequence to be equal to 1250, and to find out what is the n value, which means that the nth is this. So we have got 1000 times 1.01 to the power of n minus 1 is equal to 1250. Dividing both sides by 1000 gives me 1.25. And we did a problem like this in geometric sequences, where we said that we needed to use logarithms at this point. Rewriting this as a logarithm, we are saying that log of base 1.01 of 1.25 is going to equal n minus 1. So the n value that we want is going to be log base 1.01 of 1.25 plus 1. And we want to work out that first. Just to remind you there, 1.01 to the power of n minus 1 is equal to 1.25. I always kind of go around in this circle when I'm doing logarithms, from here to there. From here to there to there. And that's my way of working out logarithms. So let's put that into the calculator. So I want to do, just a reminder of how to do this, we want to press this button. We want to make the base 1.01 of 1.25, and then I want to add 1 to that value. 23.4. So this gives me a value of 23.4. Now that will be the point when it is 1250. So it'll actually be the year after when it goes above 1250, when they've got enough. So n is 24. That's the first year where the term would go over. That's the first term where the amount would go over 1250. So n is 24. What's the year? Try and work it out for yourself. What is the year going to be? What is the year? In what year is it? Now, you might have got 1994 as your answer, but let me show you. Here is me working it out on an Excel document. 1st of January 1970 starts with 1000. When does it go over 1250? It goes over that in 1993. So where's the mistake? The answer is 1993. But we got n was 24. Can you spot it? Right. The mistake that you may have made if you got 1994 is this. This is A1. This is A2. This is A3. This is A4. 1 is 1970. 2, 71. 3, 72. That, because 0 was the first term, that means everything's off by 1. You're kind of off by 1. 1 is 0, 2 is 1. They're off by 1, which means that 1993, this is A24. Now that is such an easy, it's such a tiny little thing, but it is such an easy mistake to make. So be aware of that. Think, what is the first term? The first term is 0. So what is the 24th term? Well, if the first term is 0, the 24th term is going to be on 23, on 23rd year. So that is what is a really common thing to make a mistake. Okay, so that's some guides and some input on how to do modelling questions. I now really recommend you have a go at some of the questions from exercise 3i. in the rest of this video, I'm going to give you some other little things about sequence series that are really useful that you might come across, and some nice little bits of information and then a challenge at the end. So keep watching after I give you these exercises for some really useful tips and tricks that are really, really useful in this chapter. Okay, I recommend these questions from exercise 3i, 2, 3 and 6, 9, 14 and 15. If you look at the date of when I recorded this video, if you're looking in the future, you might look at question 10 and be puzzled why I'm going to say this, but the people doing it now might not be that keen on doing question 10 right at this time. But it is incredibly relevant to what's going on. Okay, so I'm going to move on now to, firstly, a really, really useful identity. This is so useful. It's not something you have to know, but it can be really useful. It might look a bit daunting there, but let me show you a simpler version of it. 1 plus x plus x squared is equal to, so I'm going up to 1 plus x squared. Oh, actually, I'm just going to go up to this one. So 1 plus x is equal to x squared minus 1 over x minus 1. Or in other words, if I rearrange that, x minus 1 times x plus 1 is equal to x squared minus 1. It's the difference of two squares. But actually, if you go to the next one, 1 plus x squared is equal to x cubed minus 1 over x minus 1. That can be quite useful at times. But why is this true? It's actually pretty easy when you know what we've been doing in this chapter. And that is that, well, we're just timesing by x each time. So this is a geometric sequence with a equals 1 and r is equal to x. And all this is the sum of the first n terms. So if you take the sum of the first n terms, it's going to be 1 times r. So if I write the formula first, it's a, open brackets, r to the n minus 1 over r minus 1, which is equal to 1 x to the n minus 1 over x minus 1. And you can see that has just proved this identity. It's pretty useful. It comes up every now and so often. You might see it. So this is a useful identity to see. Okay, here's another neat little thing. This is a kind of quite a difficult question from underground maths that I found on this, and I invite you to have a go at this. I'm going to start it off. I'm not going to do the whole question. We're actually going to use this version of the sum of a sequence, an arithmetic sequence, a plus the last term. If you remember that one. So I'm going to multiply everything through by n cubed to see we have 3 plus 4 plus 5 plus ... plus n cubed minus 3 is equal to 60n cubed. And then you can spot that this is an arithmetic sequence with a equals 3, L is equal to n cubed minus 3, and n, well, annoyingly, we've got a bit of a clash here with n. So it's the number of terms that we're interested in. That can happen sometimes in maths where you get this here. This is also not the n. We might want to come and use a different letter there. Let's maybe call it p. So p is the number of terms, p. And how many terms are in that sequence? How many terms are there from 3 up to n cubed minus 3? And if you did that, then you could use Sn formula, set it equal to 60n cubed, and solve it to find that. Look on underground maths, and see if you can find the answer to this question. It's really, really a nice question. I'm actually going to tell you the answer. N is 120. See if you can get to it. N is 120. If you do, then I think that's the right answer. Okay, so the next one I'm going to say is that this is a particular problem which has one of the most really beautiful little answer to it. So it's the sum to infinity of a geometric sequence. As you can see, we're multiplying by 1 over 4 each time. And so A is equal to 1 over 4 and R is equal to 1 over 4. So it's nothing too difficult. You can see that it converges because R is between -1 and 1. And this is equal to A over 1 minus 1. So, sorry, the sum to infinity is always equal to A over 1 minus R. And this is equal to, if it converges, this, which is equal to this, which is equal to a third. So the answer to this is a third. But there is actually a really nice way of seeing why it is a third. And it's this. So I'm going to pin this here because I'm going to need to draw some squares. So if I have a square and I divide the square in 4, like so, then if I take a quarter of that square, that is going to be 1/4 of it. If I now add on to that, so maybe I shade in a quarter of this square. Okay, so this is going to be a quarter of this square shaded in this area here. This is a quarter of it. I now want to add onto it 1 over 16 because that's the second term of this sequence, 1 over 16. But another way of looking at 1 over 16 is a quarter of a quarter. That's 1 over 4 squared. So what I want to do is I want to take a quarter and I want to divide that bit into 4. And I want to take a quarter of a quarter. Well, this little bit here is a quarter of a quarter. Okay. Now I want to take 1 over 4 cubed. That's a quarter of a quarter of a quarter. Well, that means I want to take this quarter here and I want to divide that into 4 pieces. Not the most beautiful of drawings here. I want to divide that into 4 pieces. And I want to take that. So that is my 1 over 4 cubed. And I want to take a quarter of a quarter of a quarter of a quarter. So I divide that bit there into 4. And I take that there. And I take this bit here. That's a quarter of a quarter of a quarter of a quarter. And then you can keep going. And I could take that bit there. And that would be there. And now if you squint and look at this, you will see that for each section that I have done, I have shaded in a third of it. So this, a third of this region, a third of this region, a third of this region, a third of this region. And so you can see what we have done is you've summed up a third of the whole thing, and that is an explanation for why that is a third, which I think is a particularly nice, beautiful result. Okay, that leaves me with just one last thing, a real challenge if you want to kind of have a go at some really hard questions on this, and that is this. Here is some challenges, and you can pause the video or you can take a screenshot. Can you work out any of these answers? You're going to have to maybe look up on the internet about epoch time and what that is, but there's some really nice kind of results on this. But don't worry about it. This is beyond A-level maths. If you don't fancy it, you don't fancy it. But yeah, here you go. That's this chapter. I hope this has been helpful. Good luck with trying all the questions. Okay.